Welcome to a context-aware multitask running for traffic scene recognition in autonomous vehicles. My name is Yun Kwan, and this is the work I've done in GIST, which has been already accepted in Intelligent Vehicles Symposium 2020. This work is advised by Professor Eun-gu Jeon. We address the problem of visually recognizing traffic scene you are currently visiting. It is perceived as an essential key step towards understanding traffic scenes and serves to eliminate the gap between resulting performance and visual reasoning capability of human beings. For us, it might be easy to recognize the traffic scene attributes under difference in changes. However, a neural network model in the real-world driving scene, this might be quite challenging. Why is this? Well, in real-world scene, traffic scenes contain diverse scene attributes such as road place, weather, road surface, and road environment. A naive algorithm capable of performing multiple tasks simultaneously is to employ a suite of independent networks, one for each task. However, simply training a single network for a particular task, no matter how adequately optimized on each task, is far from satisfactory in terms of performance on every task. So, since they require a lot of computation per network, immediate frame-by-frame inference is very difficult. Thus, a prominent challenge in traffic scene recognition is to make a model that can operate with online frame-wise inference despite multiple tasks. The solution to this difficulty is to design a multitask running network where multiple tasks are solved simultaneously, assuming the same input. These methods rely on the sharing of the encoder's representation using autoencoder-based CNNs so that the decoders corresponding to each task can be applied to independent targets. Although previous works on the multitask running named CAMTL have made great efforts on enhancing the performance of multiple recognition tasks within limited parameters, there still remain gaps when in dynamic driving scenarios. The reason is that the sufficient contextual information from changing spatial and temporal relationships is not adequately exploited due to normally there are deeper and larger network or well-chosen hyperparameters. So the case of MTL versions, it don't happen much without considering the contextual information. So can we do something else to alleviate this problem? In this paper, we propose a context-aware MTL network based on mutual information estimation for traffic scene recognition in autonomous vehicles. Basically, we start from a general MTL-based scene recognition setting where an image classifier based on CNN framework. The core idea of our methods is to estimate mutual information constraint that calculates the lower bound between input and task-specific latent space leveraging shared encoder. To gain a fundamental understanding of efficient structure inside these visual multiple tasks, we believe that scene context illustrates the human ability to understand the scene, even though the visual signal representing the scene is disturbed or insufficient. Therefore, without complementary measures, if the shared encoder runs to operate multiple tasks, its features important. Here is where our method shines. We developed a fully neural implementation specially designed to context-aware relationships between consecutive frames and model parameters. The images are fed into the network. Shared encoder extracts latent space using mutual information constraint estimator. The task-specific decoders from the latent space utilize cross-entropy loss, respectively. Finally, the objective multitask loss function is jointly trained by multitask optimization. So then you can be able to generate contextual information and leads to higher recognition performance. Lastly, our framework is an end-to-end trainable network with a novel mutual information-based regularizer loss. So let's dive into the details of this network. We describe the details for tests of each component as follows. First, we illustrate from problem settings. we focus on the problem of context-aware MTL using deep learning in traffic scene recognition. Regarding multitask decoders, we create decoders for a total of 23 tasks, including 12 in road place, 4 in weather, 2 in road surface, and 5 in road environment. So, the multi-objective optimization for MTL using a vector-valued cross-entropy loss is illustrated as shown in slide. Then, however, it often reveals the performance of MTL is not better than single task running on the multitask dataset. To create the context-aware latent representation, we adopt an information theoretically constraint using mutual information. It encourages our encoder to extract context-aware features from the input image. Hence, the resulting latent representations of encoder would contain abundant information of input while preserving task-specific information. Then, the MTL equation can be equivalently expressed with Lagrangian multipliers as follows. However, this objective is not tractable in practice, so we give a tractable approximation by using the lower bound of information. To solve this issue, we limit the minimum value of mutual information for all tasks, and this maintains the representation specified by all tasks. Mutual information is lower bounded by noise contrastive estimation. Then, by providing the stable approximation results, mutual information can be maximized by replacing maximization in Jensen-Shannon divergence, where in equation, SP is a soft plus function. The decoder D can share backbone encoder E so that maximizing equation. This function will maximize the mutual information I. Therefore, finally can be rewritten as follows. To validate our methods, we use Honda Scenes dataset named HSD. The Honda Scenes dataset is a large-scale annotated dataset and created to enable practical scene classification. The dataset contains 80 hours of diverse high-quality driving video samples collected in the San Francisco Bay, USA. The dataset contains temporal annotations for road place, weather, road environments, and road surface conditions. All the reported implementations are based on the PyTorch frameworks, and our method has done on one NVIDIA Titan X GPU and one Intel-Core CPU. The proposed sharing encoder E is implemented as a standard ResNet 50 architecture. For the task decoders, we use a two-layer CNN with global average pooling. In this paper, we deal with 23 tasks from HSD and optimize with only one objective function equation. The last convolutional layer is pooled to a size of class categories respectively. Next is our experimental results. So then, what about the individual task? As our methods can properly be extended to deal with multitask, we compare our proposed methods with the baseline traffic scene recognition researches to probe the effectiveness. Results on HSD are reported for the following three types of models where each approach is gradually added. Option A, single task network. Option B, multitask network in baseline. And option C, adding mutual information constraint to be option B. From table 1, we can identify that expanding simply MTL network does not improve recognition performance. Especially, place category is difficult to recognize due to unbalanced dataset distribution. Therefore, when mutual information constraint is added to the proposed MTL, recognition results can be better figured in this figure, and we observe some enhancements on traffic scene recognition performance. This confirms that applying MI constraint at the same time is more helpful to capture contextual information. Accordingly, the results in this figure are the most accurate of all results. Then we demonstrate the effectiveness of our MI-based MTL approach for the application of traffic scene recognition. Table 2 and 3 show the task-wise F-scores, and the recognition performance generally outperforms the existing methods across most of tasks. This mainly due to the fact that traffic scene samples and processed with context-aware feature representations. Note that what we want to highlight in HSD is that the proposed methods can benefit from MI-based MTL framework, which captures the context-aware properties of images despite only one optimization formula and less memory volume. Here's the overall evaluation on the HSD dataset with confusion metrics. Lighter cells mean the recognition performance are higher than the dark cells. As shown in the figure 9, we can identify the proposed methods can recognize the scene attribute classes. And then figure 5, 6, and 7 indicate our method is significantly better than existing MTL-based methods. Our visualization results based on t-SNE indicate our approach proves the ability of discriminative representation, and the shared encoder can have a better context awareness ability. I'm going to conclude with some additional results on some very complicated and challenging images. So here's one. We generally address real-world traffic scenes. Despite of this fact, we are getting pretty well-recognized performance, and the number of errors is pretty minimal. And with that, I'm going to conclude. And if you have any questions, and are happy to take any questions that you have right now. Also, if you are interested in our overall self-driving project, please visit our website or QR code in the slides and enjoy our works. Thank you.